Hello and welcome to today's tutorial session. So today's problem solving session, today's session is session 10 and we are trying to focus on the some of the sample questions from the content of week 11 and mostly a few content from week 10 also. So to look at the content of week 11, we have phase velocity, then group velocity. So these are the two major topic of discussion from week 11. And then comes the field pattern of parallel plate waveguide, which we have already seen theoretically, and now we would like to look at the octave simulation. So these are the lecture content of week 11. So our discussion will mainly focus on topics phase velocity and group velocity. And this octave simulation and the related stuff has been discussed in the video lectures, and how the field pattern is being obtained with octave code. So that has been discussed in the video lectures. Please refer to the video lectures for the same. We would try to focus basically on these two topics, phase velocity and group velocity, today. So to start with, in fact, in our previous week's discussion, we have come across the basics of parallel plate waveguide. To give a basic idea of that, so assuming there are two ideal conductors which are kept in parallel to each other. So this is our parallel plate waveguide, and we say that the distance between the plates is d, and few basics which we have discussed in the last week was the cutoff wavelength lambda c is equal to 2d by m, where d is the distance between the plates and m is the mode number. Okay, and then the cutoff frequency is mv1 by 2d, mv1 by 2d. Okay, so this phase velocity, so this is the expression for cutoff wavelength and cutoff frequency. Now to come to phase velocity, Vp is equal to, let me write it like c, to make it more clear, it is V1 by square root of 1 minus Fc by F the whole square. Okay, so here the idea is, what is Fc? That is the cutoff frequency, and all the frequencies greater than Fc gets propagated. So this expression of phase velocity indicates that this phase velocity is a function of frequency. Okay, it's a function of frequency. So we have to say that, hello, hello, can you hear me? So this phase velocity is a function of frequency as per this equation. So we say that such a medium is called as dispersive medium. Okay, and this phenomenon, when the wave is, the phase velocity is uh, a function of frequency, we call it as a wave dispersion. Okay, so the phase velocity will change with respect to the, depending on the frequency. Now, if you say assume vacuum or free space, so it's a non-dispersive medium. It has a velocity, phase velocity, which is equal to c, which is the speed of light in free space, that is 3 into 10 power 8 meter per second. So vacuum or free space is a non-dispersive medium, whereas say if you have a medium which on in which the phase velocity is a function of frequency, we say that it's a dispersive medium, and this Vp is always greater than the c, or the phase the uh, speed of speed of light in free space. Now the other point to consider here is the phase velocity doesn't convey any information. So in the so in the simple case, if we say, if you have an amplitude modulated signal, a singleton amplitude modulated signal, so it's basically a combination of the carrier and the modulating signal. So we have two frequencies. One is of the modulating signal and the other is of the carrier. So you have two different frequencies and two different wave of, and on, so how we represent two different frequencies, say in case of an amplitude modulated signal, generally it's of the form like this: cos of omega plus delta omega t minus beta plus delta beta into z, plus cos of omega minus delta omega t minus beta minus delta beta into z. Okay, so this reduces to 2 cos omega t minus beta z cos delta omega t minus delta beta z. Okay, now how do we write the expression for Vp? It is omega by beta. So this is called as your phase velocity. Okay, now let me take the ratio of delta omega to delta beta. Okay, and this will be called as group velocity Vg. Okay, so this gives an idea of the difference between the phase velocity and the group velocity. Okay, so this group velocity, say in case of an amplitude modulated signal, we say that we have a modulated signal. Okay, so basically what we have is a modulating signal. Okay, and then we have a carrier. Okay, so combining these two, what we get is a modulated signal. Okay, so when you say it's a modulated signal, so that signal's velocity is your group velocity. Okay, so that is where the information is being carried. Okay, so that group velocity is the one which conveys the information. Okay, so we say, I can just try to refresh the concept of modulation. So if you remember the very basic idea of modulation, so here you know that this is the envelope. Okay, so this, whatever I am just trying to, so this is our envelope, which is a modulated signal. Okay, so you have a carrier and you have a low frequency modulating signal. Okay, so this is your modulating signal and this is your carrier, and product of these two gives you the modulated signal, which will have an envelope like this. Okay, so that is going to be the, So that so this envelops velocity. Okay, so the velocity of that modulated signal or velocity of that envelope, okay, that is your group velocity. Okay, so that is the whole idea of group velocity. So to make it more uh, clear, so Vg is written as d omega by d beta. Also, Vg can be expressed as V1 into square root of 1 minus Fc by F the whole square. Okay, and also we know that Vg is less than V1. Okay, Vp is greater than V1, or C, whatever it is, so, and Vg is less than V1. So group velocity is always less than the V1, whereas phase velocity is always greater than V1. Okay, and if I would like to just point out one more thing, which is already discussed in the video lectures. If you remember, the for the different modes, Vp. So this is the graph of Vp, and this is the graph of Vg. Okay, Vg. So Vp versus or Vg versus frequency. Okay, so this is the graph. Now I would like to give some hints on our upcoming assignment. We'll discuss the questions. We'll not discuss exactly how to do it, but we will try to give some comments and hints. Okay, so you see the first question of upcoming assignment, which is due on 12th of April, that is the coming Wednesday. So you have the very first question. You see which of the following statements are true. So the question is on fundamental mode is a non-dispersive mode of a waveguide. TE10 is the fundamental mode of a waveguide, rectangular waveguide. TEM is the fundamental mode of parallel plate waveguide, and all of the above. Okay. So you see the discussion is on basically on the fundamental mode or a dominant mode. Okay, we know what is a dominant mode, the mode with the least cutoff frequency, and which is that in case of which mode is the in case of dominant mode, in case of a rectangular waveguide, which mode is called as the fundamental or the dominant mode. That is the idea. And you must be knowing what is TEM, what is TE. So TEM is the transverse electromagnetic wave. So you should know whether it exists in a rectangular waveguide or whether it exists in a parallel plate waveguide. So all these ideas will give you a clue of how to answer this question. So, and one important thing which I have discussed right now, what is a non-dispersive medium, or what is a non-dispersive. So dispersive, non-dispersive. So dispersive means so the phase velocity is a function of frequency, whereas non-dispersive means it's the phase velocity is non-dependent on the frequency. Now coming to the next question in this row. So if you see, there is a, for a 54 centimeter long pure flint glass filled, n is equal to 5 by 3. So that is the refractive index of the flint glass. Okay. So there is a pure flint glass with this refractive index. The parallel plate waveguide with the distance between the plates. So it is a question on parallel plate waveguide. So the distance between the plates is given as 5 centimeter, and you see the highest supported mode TE3 has a phase velocity 3 into 10 power 8 meter per second. So now you can understand from the question that the phase velocity is equal to 3 into 10 power 8 c. Okay, 3 into 10 power 8 meter per second, or which is nothing but the c. Okay, and you see the highest supported mode. Okay, so base depending upon the uh, parallel plate waveguide, the highest mode which is supported in this is TE3. TE is transverse electric, and 3 is a mode number. Okay, so mode number M is equal to 3, and we also know the distance between the plates. Okay, now we will be able to find what is the cutoff frequency or cutoff wavelength if you know the uh, distance between the plates and also the mode number. So we know the equation Fc, or lambda c, is equal to 2d by m. So once if you know d and m, we can calculate the cutoff wavelength. Similarly, we can also calculate the cutoff frequency. Okay, so now the point is, let's look at the questions. Single mode operation is guaranteed till the maximum operating frequency. So single mode operation, in the sense mode number m is equal to 1, is guaranteed till the maximum operating frequency. So we need to find the operating frequency. So, and we know that we need to see for m is equal to 1. So for m is equal to 1, what is Fc? Okay, V1 by 2D. Okay, so once you know that, that is your cutoff frequency, and that is now you see till what operating frequency a single mode operation is being guaranteed. Now, next question is on the cutoff frequency of the TE3 mode. So cutoff frequency, you must be knowing the equation for cutoff frequency, and you see the mode number, what is to be substituted, and then find out the cutoff frequency given for a given plate separation. Next question is for operating frequency. Definitely that can also be found. Now next is phase velocity for the fundamental mode. Okay, which is the fundamental mode? Then find out the phase velocity of that particular mode. Then group velocity, yes, you can find out. So in case of phase velocity and group velocity, the idea is use the expression Vp. Phase velocity is Vp is equal to V1 into root of 1 minus Fc by F the whole square, whereas phase velocity expression is c by root of 1 minus Fc by F the whole square. Group velocity c into root of 1 minus Fc by F the whole square. Okay. So this based on the mode number we need to find. Okay, fundamental mode, you should know what is the mode number to be kept. For a given mode, please substitute the mode number, appropriate mode number to find the corresponding group velocity. Okay, so once you know the mode number, it is easy to calculate the cutoff frequency of that particular mode and then use the expression to find the Vg. Okay, assuming only waveguide dispersion, group delay between the fundamental mode and the DE3 mode. Okay, so this question is on the delay between fundamental mode and the DE3 mode. So uh, once you know the Vg for fundamental mode and you find out the Vg for TE3 mode, okay, for a given length of the waveguide, you see the length of the waveguide is 54 centimeter. For that given length, you can always calculate the time delay. Okay, so use the basic expression. What is time delay? Time delay is, so based on the velocity, okay, velocity is equal to distance by time. So this velocity should be the group velocity. So group velocity is equal to the length of the waveguide divided by the time delay. So time delay you can calculate by length of the time delay can be expressed as a ratio of length of the waveguide to the group velocity. Okay, so once you know Vg1 and Vg2, whatever it is easy to find the time delay between these two. Okay, so then the ninth question, if you see, group velocity for the TE3 mode at twice the operating frequency. So you take the operating frequency, twice the operating frequency, and you try to find the group velocity for the TE3 mode. Again, so operating frequency is nothing but F. FC you have to calculate based on the mode number and substitute in the expression for group velocity. Okay. Coming to the last question, cutoff frequency for the TE1 mode in air-filled parallel waveguide is known to be. So see the in the question what is given is for TE1 mode there is a cutoff frequency that is given in the question. For this waveguide used at a wavelength of lambda equal to 1 centimeter, the group velocity of TE2 mode is. So wavelength of lambda. So you see the group velocity of TE2 mode. Okay, group velocity of TE2 mode, you have to use Vg's expression. In Vg's expression, you have to substitute Fc and F. So what to substitute for that Fc and F? So Fc should be based on the mode number here and F should be based on this particular wavelength. This is the operating wavelength. So from operating wavelength, we can definitely calculate the operating frequency. Okay. So these are some of the hints to use to solve these assignment 11. Now we will try to discuss a few similar questions uh, to give a basic idea of parallel plate waveguide and how to solve some of the questions from the parallel plate waveguide. Okay, now let's move on to a discussion of one question. An air-filled parallel plate waveguide carries TM2 mode. Okay, so we have a parallel plate waveguide, that means two ideal conductors, okay, with air filled in between, okay, and say the spacing is D, and you have a TM2 mode, okay. So this is the mode of operation. Now the height of the waveguide, or we can also call it as the separation between the plates, that is 30 centimeter. If the phase velocity of the mode is 1.2 c, so that is your phase velocity 1.2 c. Find the frequency and guided wavelength of the mode. Okay, so you need to find the frequency and you need to also find the guided wavelength of the mode, Vg. Sorry, guided wavelength is lambda g. Sorry, lambda g. So from the given thing, so we can say that the mode number m is 2 and the separation d is 30 centimeter. Now can you calculate the cutoff wavelength or cutoff frequency? So cutoff frequency Fc is m v1 by 2d. Okay, so m is 2 into v1 is the speed, because it's air filled. We can say that it is 3 into 10 power 8 divided by 2 into plate separation d is 30 centimeters. So let me make it like meters. In meters it will be 0.3 meters. Okay, so once if you do this calculation, what we get is 10 power 2 gets cancelled and 3 and 0.3 gets cancelled. Into 10 power minus 1. So this becomes 10 power 7 gigahertz. Sorry, 10 power 7 hertz. So we can write it as 10 megahertz. Okay, so that is your cutoff frequency for the TM2 mode. Okay, this is the cutoff frequency of TM2 mode. Now, what is VP of this mode? Okay, for this TM2 mode, we can always calculate VP. What is the expression? C by root of 1 minus FC by F the whole square. Okay, so that is nothing but 1.2 times C. So C gets cancelled and 1 minus FC by F the whole square is equal to 1.2 square. So this is 1 by 1.2 square. One minus 0.694, that is 0.306, which is Fc by F the whole square. Take square root of this. Taking square root of 0.306 is 0.553. Fc by F is equal to 0.553. So F can be written as Fc is 10 mega, so 10 power 6 divided by 0.553.
So F will be calculated as 10 divided by 0.553, that is 18 megahertz. Okay, 18 megahertz. So that is your frequency. And how do you calculate lambda g, the guided wavelength? Lambda g is equal to Vp by F. What is Vp? Vp is 1.2 times C. So 1.2 into 3 into 10 power 8 divided by what is F? 18 megahertz. So 18 into 10 power 6. So if you simplify this, you will get it as 1.2 into 3 divided by 18.2 into 100. So that is your 20. Okay, so this is 20 is your guided wavelength. Moving to the next question here. Find the cut in the previous question. Find the cutoff frequencies of TM3 and TE4 modes. How many TE and TM modes will propagate in a waveguide at 6 gigahertz? Okay. So TE or TM mode. So how do we find the cutoff frequency? So the basic expression for cutoff frequency is mv1 by 2t. So for any mode m, let us make it generalized. So m into, because it's air filled, we can write it as 3 into 10 power 8 divided by 2 into the plate separation was plate separation of the previous question was 20 centimeters. Isn't it? Okay, 30 centimeters. Okay, so let us write it as 30 into 10 power minus 2. Okay, so this comes out to be 5 m into 10 power 8 hertz. Okay, or we can write it like 0.5 m gigahertz. Okay, 0.5 m gigahertz. So for any mode m, so the cutoff frequency can be just substitute, you just substitute the value of m multiplied by 0.5, that much gigahertz will be the cutoff frequency of any mode m. Say in case of TM3 mode, you just have to substitute m value as 3. So 0.5 into 3 gives you, so 0.5 into 3 gives you 1.5 and 1.5 gigahertz. So TM3 mode has a cutoff frequency of FCS 1.5 gigahertz. Similarly, for TE4 mode, substitute m is equal to 4. So 0.5 into 4 is 2 gigahertz. Okay, that is for TE4 mode. So that is your TM3 and TE4 modes. These are the cutoff frequencies. Okay. So that is the first part of this question is being answered now. The cutoff frequency of TM3 mode and TE4 mode. So once you know the mode number, it is easy And you must know the plate separation, and you must also know whether it is air filled or not. If it's air filled, we can directly write the velocity as 3 into 10 meter per second. Okay, so that's how we found the cutoff frequency of TM3 and TE4 modes. Now the next question is, how many TE and TM modes will propagate in the waveguide at 6 gigahertz? So at 6 gigahertz, so now the operating frequency is 6 gigahertz, and you need to find how many TE and TM modes will propagate in this waveguide. Okay, so find out that so any mode which has a cutoff frequency less than 6 gigahertz. Okay, so let's write it like this. So any mode's cutoff frequency is what? 0.5 m gigahertz. So any mode with the frequency, so any cutoff frequency less than 6 gigahertz. Okay, 0.5 m should be less than 6. So in that case, m can be found like this, 6 by 0.5. Okay, so which is equal to 12. Okay, so since the cutoff frequencies we have, so there are 12 modes which propagates. Okay, so when we say 12 modes, it is, there are TE and TM. So in case of TE and TM, let's see how the 12 modes are. So one is TE1 to TE11. Okay, so it's not 12 modes. This expression means that m is less than 12. Okay, so when m is less than 12, which means up to 11th mode. Okay, so TE1 to TE11 mode. Similarly, in case of TM, there is TM0 to TM10 mode. Okay, so these are the TE and TM modes which propagates. Okay, so the idea here is very clear. Any cutoff frequency less than this particular operating frequency will propagate. So based on that, you find the value of m. So we see that m is less than 12, which means m can be up to 11, from which we write the TE and TM modes. Now let's move to another question. The next question is, a parallel plate guide is to be constructed for single mode propagation. So when we say single mode propagation, idea is clear, m is equal to 1. So that single mode propagation is for frequency less than 3 gigahertz. Okay, for frequency less than 3 gigahertz, it's a single mode propagation. Given the dielectric between the plates has a relative permittivity of 2.1. So that is epsilon r is equal to 2.1. Determine the maximum allowable plate separation. Okay, what is D max? Then next question, find the electric field inside the waveguide if the magnetic field for this mode is 0.2 ampere per meter. Okay, so to start with the first part of the question, so TM mode exists in parallel plane. So in case of TM0, okay, TM0 mode, the first higher mode is TM1, okay, when m is equal to 1. So first higher order mode is when m is equal to 1. That is, say, for m is equal to 0 and for m is equal to 1. So for m is equal to 1, the cutoff frequency Fc is, so the general expression is mv1 by 2d. So we can write it as So when we say a very important thing to remember here is V1 is equal to C only when it's an air-filled guide. Okay, but if it is a wave, if it is a wave parallel plate guide filled with some dielectric, okay, dielectric filled wave guide, then we have to express it as C by root of epsilon r. Okay, so this is your 2.1 is your relative permittivity, so C by root of epsilon r. So let me make it clear. V1 by root epsilon r 2D. Okay, so for that Fc is V1 by root epsilon r 2D. Okay, so D is equal to V1, which is C, 3 into 10 power 8 divided by 2 into D. Distance between the plates is being found. So Fc root epsilon r is to root of 2.1 into Fc is Fc has to be taken as 3 gigahertz. So 3 into 10 power 9. So for the single mode propagation to happen, what is the maximum allowable separation? So once if you solve this, you will get. So please understand that Fc is the cutoff frequency. Okay, and we want a single mode propagation for frequencies less than that 3 gigahertz. So make it 3 gigahertz. So make this as the Fc. Okay, then what is the allowable, maximum allowable plate separation? So if you calculate this, you will get 3 and 3 gets cancelled and 10. So 1 by 2 into root of 2.1 into 10 and 1 by 28.9 gives us almost 3.46 centimeters. Okay, so that is your maximum allowable plate separation. Now the second part of this question, find the electric field inside the waveguide if the magnetic field for this mode is 0.2. So the magnitude of magnetic field is given as 0.2 ampere per meter. Now the question is on what is the magnitude of electric field. So what is this related by? So we have an expression for eta which is mod E by mod H, where mod E and mod H are the magnitude of electric field and magnetic field. Okay, and we know how to write the expression for eta. Okay, eta expression is dependent on the whether it is a dielectric field or not. So how do we find that? Eta, say if it's a dielectric field thing, then we can say eta naught by root epsilon r. Okay, so we can equate here eta naught by root of 2.1. So now we know what is H, find out E. Okay, E is equal to 120 pi by root of 2.1 into mod H. What is mod H? 0.2. So simplifying this, 120 pi into 0.2 divided by root of 2.1 gives us 52. So that is your magnitude of the electric field, which has a units volt per meter, 52 volt per meter. So that's all with this particular question. Coming to our discussion, back to our discussion on the next question. Parallel plate waveguide has a height of 2 centimeters. So here it's a D is 2 centimeters and filled with a dielectric of relative permittivity 2.25. Epsilon R is 2.25. Magnetic field inside the guide. Okay, so this is your magnetic field. So this you see, this is the magnitude of the magnetic field, and this is omega t minus beta z. So determine the mode that is propagating, and second question, what is the phase constant? Okay, now coming to our discussion here, mode H or the magnitude of H or mode H is 50 ampere per meter. Okay, and we know that this is omega t minus beta z of the form of that. So omega is 3 pi into 10 power 10. Okay, then and this is of the form, say generally the magnetic field or electric field expressions are of the form m pi x by d, cos of m pi x by d, where m is the mode number, x is the location or specific location, and d is the plate separation. Okay, so when we say cos n pi x by d, so this is along x direction and d is the separation between the plates, where m is the mode. So if you equate this to this, we can say m pi x by d is equal to 100 pi x. Okay, 100 pi x. So from that I can write m pi by d, sorry, pi can be cancelled. So m by d is equal to 100, or m is equal to 100 into 2 centimeters, which is 10 power minus, converted to meter, it will come 10 power minus 2. And m is equal to 2. Okay, that is your mode number. So here you know the mode number and you also know the angular frequency. Now, second part, so the first part of the question is now already answered. So that is just look at the expression for magnetic field and then conclude what is the mode number. Okay, so to conclude about the mode number, we need to understand that this second part is of the form cos omega t minus beta z, and the first part is of the form cos n pi x by d. Okay, so cos n pi x by d gives us what is the mode number. Okay, so equate it to 100 pi x and you find out the mode number here. Then coming to the discussion on phase constant beta, the second part of this question. To come to that, what is phase constant in case of a parallel plate waveguide? Beta bar is equal to beta into square root of 1 minus m lambda by 2d the whole square. Okay, so from this expression, beta into root of. So this beta has to be first found and then multiplied by square root of 1 minus m lambda. So m is the mode number, again it's 2, and m lambda by 2 d the whole square. Okay, so here beta, you have to find out what is beta. Beta is 2n pi f by c into square root of 1 minus mc by 2n df the whole square. So you see n is nothing but the root epsilon r. So please don't confuse. Basically, if you have velocity c, so c by root epsilon r is the actual velocity because it's a dielectric field guide. So c by, instead of saying c by root epsilon r, we can also say c by n. So that's how we get this c by n in this expression. So basically, what if you see what is the expression for beta? Beta is basically 2 pi by lambda. Okay, so we can replace lambda as c by f, or velocity by frequency. So 2 pi velocity v by f. Okay, now next step, we will expand this with the specific velocity. Okay, so 2 pi by v can be replaced as c, by root epsilon r is n, and this is f. 2 pi nf by c. 2 pi nf by c. So this is your beta. Okay, once you know the beta, you substitute it here in this expression. Based on that mode number also, you have to use the mode number, and the lambda wavelength also you need to calculate. So basically lambda is nothing but again v by f. So let's see that. So basically here lambda is v by f, or I can say c by nf. Okay, so that lambda has to be substituted here also. Okay, and d is in the question. D is 2 centimeter, and m is already found in the first part, that is 2, and beta will be found from here. So substituting all this, you can calculate and come back to beta. Okay, once you calculate and come back, you must be getting beta value as, you see, 351.24 radian per meter.